Hi, everyone. Welcome to the a16z podcast. Today's episode is with one of our newest portfolio companies, which is applying nanoscale material science to fruit and vegetables. In this episode, we cover everything from how that affects what we taste and what we see at the grocery store, to farming and both local and international food supply chains, to how nature, the ultimate complex system, works. And then more generally, we talk about how material science's advances are playing out differently today, thanks to a few interesting things. And just why I heart material science so much. We have with us today a16z partner Malinka Walioladi and James Rogers, who is the CEO and founder of Appeal.
Formerly Appeal Technology and now Appeal Sciences.
And that's Appeal with A-P-E-E-L, not A-P-P-E-A-L.
We like our puns.
Well, it's really appealing and interesting what you're working on. Sorry, I couldn't resist.
Like your puns
I couldn't resist.
Well, I hope we have a fruitful discussion.
Oh, no, God, stop right there.
Sorry.
The investment memo that I wrote up was full of puns. I actually spent extra time thinking about
Are you
apples
serious?
to apples or avocados to avocados.
You did not.
Yes, I did.
Okay, let's talk about the fact that the graphs on their slide, this is what I noticed, were color-coded by the fruits. And so, okay, we're giving a lot of insider knowledge. Let me just tell our audience what the hell we're talking about, which is that you guys work with food technology. And in particular, one of the first products that you guys have out is a protective layer. Actually, I'll let you describe what your product is.
We use food to preserve food, which sounds really abstract. And so to make it more tangible, effectively what we do is we take uneaten plant material, so things like stems, leaves, grape skins, orange peels, banana leaves, whatever is available. We blend those things up, and then from those blends, we extract very particular subsets of molecules.
When you say you blend those things up, it sounds like a smoothie.
Yeah, it's not half a banana and a quarter of a strawberry or something like that. We actually know down to the isomer what these materials are when we create these blends. We then extract those really particular subsets of materials. We turn them into powders, so they're lightweight, they're low cost to distribute. And then we ship them to wherever we'd like to use them. We reconstitute them in liquid form, and we dip fresh produce into that solution, and we allow it to dry.
So first of all, does that mean I'm going to be eating like a strawberry that's like covered in this weird material?
What's actually happening is what we're doing basically is taking materials from inside of that strawberry, the structural building blocks, the components that give the produce its actual structure. We're extracting those, and then we're reapplying them to the outside of the produce. And so the materials we actually apply are imperceptible.
So I wouldn't taste it.
Yeah, you can't taste it. It actually tastes much closer to the fruit when it was actually picked originally.
What it's really doing is providing a protective layer that preserves its shelf life and its freshness.
That's exactly right.
I'm asking about strawberries in particular as an example, because the one thing I know about strawberries apparently have the highest concentration of pesticides of any fruit. Like you have to wash it 3 times, and I'm OCD, so I wash my strawberries 5 times to get the disgusting layers off to make it fresh and healthy.
Yeah, it's really tough. I mean, strawberries are in a really difficult position. And actually, a lot of agriculture is this way, in that the way that we grow food, the way that nature produces things is through a systems approach. It's got this huge complex system, and part of the system is growing things, and part of the system is breaking down things and recycling them. And it's got this whole machinery that's built up. The problem is for us in commercial agriculture, we don't care so much about the breakdown. We don't really care about the system diversity. We just want to contain as many variables in that system as we possibly can. And so what you end up doing in things like strawberries in particular, really sensitive, delicate fruit, is that even before you get started, you go out and you tarp the field and you hit it with something like, methyl bromide or chloropicrin or, hot steam, which just carpet bombs everything that's in the soil. And now you're able to plant your fruit, and so it won't be attacked by any of those things that were out there naturally. But that leads to the ability of certain pests and pathogens to get into that system because there's no kind of natural defenses that are out there. So
fascinating.
So it's really kind of interesting. By solving one problem, you create other problems. Long-winded way of saying there is significant amount of pesticide usage that's just required in order to get you fresh, high quality produce to your table currently. The trick about what we're doing is that it's not some sort of synthetic material that nature's never seen before. We're just using the exact same building blocks that nature uses every single day, and we're simply repurposing them for a different application.
So I want to say something that's probably not very popular in this room, which is that sounds like a high-class problem to me, because I've been to countries where you actually don't get a lot of fruits and choice in what you eat. You actually can only get certain items certain times of year. And so it's like certainly very useful. It's preserving food, but like, what is the benefit overall? Like when you think of the food ecosystem as a whole, like what does it really do for us?
So it's interesting, you know, say it's a high class problem, and indeed, you know, preserving fresh berries is definitely a high class problem. You know, if the joke at the retail level is that the berry consumer spends twice the number of dollars in the grocery store as the non-berry consumer,
is that
and
true?
so according to Driscoll's, that's true.
Wow.
And so so in that sense, yeah, absolutely, you could actually put numbers to it. Preserving berries is a high class problem. The interesting thing about that, though, is that perishability affects every single kind of produce on this planet. And that means that it's either feast or famine in most parts of the world, particularly if you're a smallholder farmer, you're only growing one type of crop. So my example I always pick on is, you know, if you're a mango farmer in the developing world, and
I love mangoes, by the way. That's my favorite thing in the world.
If you're from South Asia, you have to love mangoes.
Yes, exactly. And they're so seasonal. You can only get them at certain times of year.
Really tricky.
But anyways.
So the problem with perishability is really that everything is seasonal and it's also perishable. And that means that if I'm growing a particular commodity in a portion of the world that does not have access to a market where I'm able to turn that commodity into money, then it doesn't even matter if I'm growing that food. I'm not able to earn economic returns for my labor. And so what ends up happening is you end up having nature doing its thing, growing all of this produce that's inherently valuable. But because of the perishability, because of the inability to get that produce from the place that it's produced to the market where someone's actually willing to pay for it, you return none of the economic value for your labor. So it's all about market access.
So in the case of mangoes, if I'm a farmer in India who's growing mangoes and I am a consumer in the US who wants those mangoes, currently I probably really can't get them.
It comes really down to transportability and transportation costs. So, for example, in the case of avocados, the price of shipping a box of avocados to China is more expensive than the box of avocados itself, because of perishability, you have to air freight them in.
It's not just the distance and the cost, but because of the perishability, it requires a
certain mode of transportation. So, and you can look at it in really interesting ways. I mean, the way I always think about the world is that, again, I keep going back to this, all produce is seasonal and it's also perishable. And so you can look around the world around where produce is available at different times of year where it's able to be grown. And then you know the overall shelf life of that commodity. And you know how fast a boat can move. You know how fast a plane can fly. And so you can draw basically, a circle around those production regions and show where produce is available basically at what cost throughout the year. What we're able to do is dramatically extend the shelf life of that produce, which dramatically expands the overall radius of availability of fresh produce, which opens up new export markets for customers.
That actually goes in both directions too. If you're a grower in California or the Midwest, you can now sell to China, like your avocados.
Oh, yeah.
But on the flip side, if you're a grower in India who has avocados, you can now sell them to California or the Midwest or anywhere else.
You're totally correct that this absolutely goes both ways. And it's actually really fortunate that it goes both ways, because if you're a smallholder farmer out in the middle of nowhere and you've got 1,000 mangoes and your neighbor's got 1,000 mangoes and your other neighbor's got 1,000 mangoes, you can't sell a mango to your neighbor to save your life.
Just a race to the bottom, because you can't. You have no margins,
and they rot,
right?
And they just rot, and that's it was said to me once, for fresh produce, the tyranny of time, and that really resonated with me, because if you think about the position a smallholder farmer is in when a trader comes to them, that trader has the best leverage in the world, because they know that they can just sit outside the farm until the mangoes rot, and then say, well, you either sell them to me now or sorry, I'm leaving. And so the smallholder farmer's often left in a situation to say, well, I can either earn 2 shillings per mango or nothing. And what we found in talking to smallholder farmers is that if you can extend the shelf life of a mango by an extra week, they can earn an extra 3 to 5 shillings per mango. So it's amazing, right? You think about being able to, just by preserving produce an extra week, be able to earn 2 to 3 times more for that exact same commodity. That's a dramatic improvement in the amount of economic value those smallholders are able to capture.
So, a few times you've mentioned small farmers. Let's talk about the economics of farming in general. and produce and food. So people talk about big food with a capital B and a capital F. I know there's a lot of politics around that topic, but politics aside, what does the ecosystem for farm and food production look like? There's small farms, there's middlemen, there's big farms. Like what's the landscape?
I mean, generally speaking, right, there's producers, which is a large number of disaggregated, relatively small farms. There's some huge farming operations, but a bunch of really disaggregated small farms. And then there's a relatively concentrated number of grower shippers that typically grow some portion of the crop that they're shipping, but then they aggregate or buy from a bunch of those disaggregated growers. Then there's the grower shippers who are handling most of the transportation. And then there's retailers, basically. Those can be food service channel or just a general retailer. And then there's really the end consumer. There's some kind of side alleys in there and kind of different niches, but that's kind of the general organization.
The problem with some of these, they just don't have the electricity, whatever infrastructure to support cold storage. The way you extend the shelf life of fruit is via cold storage.
I'm super happy you brought that up, Malinka, because if you look at spoilage rates in the United States, and the numbers are kind of all over the place, but they're between a third and a half of what we're growing.
Holy shit. That's a lot
it's
of
ridiculous.
Bad food going bad.
It's particularly ridiculous when you consider the amount of resources that go into producing that food, right? The numbers are around 80% of fresh water going into irrigation, all of the pesticide usage that ends up, running into the water streams that's putting pesticides on fruit that we're not even eating, all the human capital that goes into it, all the fertilizer, all this stuff. And then ultimately a massive, massive amount of it's ending up in a landfill. And the funny thing about that, and it's actually horribly unfunny, is that that's in the US. We've got this incredible technology and incredible supply chain. And the way that we've been able to get down to, a third or, 40% of our produce being thrown away is that we've been able to use refrigeration. We've been able to use low temperature technology to basically slow everything down inside the fruit. And that works. That's work that's gotten us to about, throwing away a third, if you call that working. Now, so you start talking about trying to be able to reduce losses, which can be, 80, 90% of a harvest in the developing world. If you want to just piggyback off what we've done in the quote unquote developed world, you're trying to say, oh, well, everyone should just implement a cold chain. Well, that's really hard to tell a farmer to do in the developing world, where there's hardly roads, let alone an electricity grid, let alone the capital equipment necessary to do the refrigeration. And so I often think of it as distributing, refrigerators in a packet to treat their mangoes and get an extra 10 or 15 days of shelf life out of those without needing to do all the infrastructure development necessary.
I love this theme. We, did a podcast recently on drones in Africa, and it is about how certain technologies can help you leapfrog the lack of infrastructure and essentially create this gonzo infrastructure, essentially. And it's interesting. It plays out from both mobile, where you have entire countries leapfrogging existing PC infrastructure to go to mobile straight and be mobile first. In this case, like in the case of zipline and drones in Rwanda, it's literally leapfrogging that there's a lack of roads and
medical infrastructure. Yeah. I literally was thinking on the same lines, which is using technology to compensate for the lack of traditional infrastructure, right? Like with zipline, you're having them drone deliver medical supplies to compensate for the fact that they don't have roads and medical infrastructure. You guys are compensating with your technology for the fact that they don't have, electricity, cold storage infrastructure. You mentioned mobile. It actually does all link together. That's really
it does, but it's fascinating that you use the word compensate, because yes, technically it is a sort of compensation. But I think the interesting thread to me is that it's actually an opportunity for an entirely new system that bypasses existing systems. It's actually a way to go outside. And when you think of like the full stack startup, I mean, not to get all crazy riffy, the thing that's really interesting that makes companies like Lyft and Uber work versus the traditional taxi services companies, according to Chris Dixon's full stack, startups thesis, is that you're essentially bypassing existing systems in order to do it. So it's just a really fascinating theme in general when I think about how innovation happens.
Oh, yeah. I mean, that's exactly how I think about it as well. One of the ways I look at our product as well is infrastructure in a packet. You've got really poor roads, and now you're able to get that produce a certain distance before it goes bad. Well, if you double the shelf life of that produce, it's effectively like doubling the rate that you're able to travel on that road, if you kind of think about it that way.
And essentially opening up entirely new ways of competing with people who have an entrenched position in existing infrastructure.
Absolutely. And the other, I think, interesting point around that is what we've done in the United States is that we've built up these supply chains around the intrinsic constraints of the piece of produce. And this whole supply chain has been established just understanding this is the limitation of that piece of produce.
Yep.
You show up in Nigeria and you give somebody a packet of material that's able to make their tomato last twice as long. They're not going, how does this affect the temperature that I'm supposed to store my tomatoes during cold storage?
Right. They're not locked into that existing supply chain system.
And you're actually building from scratch as opposed to trying to wedge into an existing supply chain. So although it's difficult and challenging for particular reasons to deliver these technologies into developing countries, the white space or the opportunities are actually really, I think, an interesting kind of proving ground for what the ultimate power of the technology really can be.
I agree. And it's redefining technology to me in an interesting way, because when I think of the typical cold chain, I remember anecdotes from companies that were doing like thin film electronics, and they would do like these sort of thin film disposable sensors as a way of putting really cheap RFID tags in order to tag the status of where it is in the supply chain and keep a certain temperature level and be able to monitor it continuously. And there's all these interesting, probably very useful, complicated technologies in the existing system. But what you're essentially doing is bypassing that with an entirely different, very natural form of technology, which brings me to my next question, which is, what is the technology in the quote traditional or non-traditional sense that we're talking about here? Because it's kind of interesting. Like you're essentially describing shredded plant parts.
I think there's just an important distinction to be made, and that classically the technologies that we employ in agriculture, I think, are what I've kind of gone through this kind of mental exercise of what is a chemical and what is a molecule. And
that's a really interesting mental exercise.
Yeah, right. Well, for nerds, I guess.
Why does the difference between a chemical and a molecule matter?
And this is my definition, but what I've landed on is, for millions and millions of years, nature has used the same building blocks, and it's just basically broken them down and recycled them into different forms.
Very efficient thing for nature. It to do.
An incredibly efficient thing. It's actually, one of the only, non-zero sum games that I can really think of. I think it's beautiful and elegant the way that it's been put together. But it's done pretty damn well without us for millions and millions of years. And then we came along and said, oh, nature, you've got these beautiful, well thought out, systems in place. And what we're going to do is we see the mechanism that you're using to do that, and we're going to develop a new chemistry or a new molecule that's going to interfere with that particular machinery. The problem is that those processes that we generally interfere with are really valuable processes. That's why they've stuck around for so long. And so they're used by many, many, many different types of life forms. And so it's incredibly challenging to poison one bug without poisoning every single bug that's out there, even the good ones. What nature's done is not generate, kind of a poison to kill things. It's you use the exact same molecules. It's just combined them in different ways to form different structures. And those structures generally provide protection from the external environment, whether it be the scales on reptiles or the skin on the leaf of a plant.
It's like a whole new form of combinatorial innovation.
If that's what you're saying in Silicon Valley, then that's exactly what it is. I mean, in a way, there's a lot that goes into it. And empirically, actually, like, this is not a new idea what we're doing, right? Monks discovered in the Middle Ages that you were able to dip apples in beeswax and they would last throughout the winter. That was a pretty incredible innovation at the time, especially considering lack of access to refrigeration.
The same thing is true of beauty products, like being able to layer on layers of oils, or it's the same kind of thing with skin and preservation, because skin is perishable.
Skin is very perishable. Actually, probably the number one question I get is, can I use this on my skin?
I was about to say, when I saw your pitch, I was like, my mind immediately jumped into all kinds of makeup products.
Yeah. It's a really interesting future product line. Nature has provided us this incredible toolkit of different molecules that are available to us, and that us as material scientists are in a fortunate position now with today's technology to be able to isolate those materials from nature, look at them as if they were a Lego and say, what would this be useful for? And what if I combine it with this other Lego and I let these things dry together, will they form a structure that could give me some really interesting properties?
What are some of the, I mean, that's when you say that way, it's a beautiful, simpler explanation of what you're doing. But actually what you're doing is actually pretty complex and complicated. It requires a lot of hard science. What are some of the challenges you have to overcome to be able to create those Legos and building blocks, or combinatorial innovation, as I would call it?
So for me to be able to sit here and abstract to the 30,000 foot level of analogy of Legos, I have to have a team of 62 very, very talented individuals composed of, over 50 scientists and 15 of those are PhD scientists.
All in material science or different?
Across disciplines.
Okay.
Chemistry, biochemistry, material science, chemical engineering, mechanical engineering. So across a wide range of disciplines, and it actually requires each of those disciplines, because one discipline is looking at how do we extract these materials, how do we purify these materials, which is one discipline. How do we take and confirm what these materials are, which is analytical chemistry. How do we then combine these things in different ways to form interesting structures? That's material science. How do we analyze these things? That's more in the physics realm.
Oh,
how do we have enzymes make these things for us? That's biochemistry. So
I'm going to come work for you.
You should definitely. It's really incredible. But what we've been able to do basically is rally this group of incredibly talented people around this core focus of leverage nature's operating system to solve problems that nature's solved before, basically by just blatantly copying what nature's doing.
A lot of people sometimes, I feel, they overuse that analogy of an operating system, but I think in this case, it really applies. I mean, there is no other way to describe it.
Well, for us in the physical realm, like nature's operating system are the laws of physics, and we just want to use that system, understand as much as we can, and then take pieces and let the operating system operate on them. It feels like a different type of X-ray vision, where instead of just looking at the object and seeing, okay, that's a water bottle, knowing down to the molecule what it's made out of, why it has the properties it has, and how you could impact those properties by changing what the water bottle is made out of.
It's not unlike how artists or photographers see the world differently when they paint or capture it on film. You just look at scenes very differently because you bring your craft at a very deep X-ray level.
That's cool. We got some materials artists.
Yeah, it's very artistic to me. At the end of the day, what you're doing is super interesting. So what are some of the other challenges?
I think it's iteration cycle, frankly, when it really comes down to it. I love programming computers because I'll write some code and I'll get a debug error. It says you did something wrong. You need to fix it. The challenge in material science, I'm just broadly speaking about material science here, is when you want to hit compile, it might mean 6 years of PhD work to compile the system that you might get one data set out of. And that iteration time really kills a lot of, I think, companies that are looking at getting into a materials-based company.
How do you guys overcome that? I mean, you can't bypass it altogether.
So a number of members of my team, spent their PhD basically learning different technique development to basically access some new understanding of some fundamental set of molecules. And so I think at our core, we have this kind of respect for not just using off-the-shelf technology to get general information, but really committing to understanding and learning a new technique or developing a new piece of equipment that can help speed up some of those iteration cycles in material science. If you come by and visit our office, you'll see a large number of analysis systems that we've built ourselves, that we've had to make the investment of time and money in, that you would say, well, oh, no, you just need to keep hitting the fence. But when you're just hitting the fence and you don't have that feedback mechanism, then you can't tighten that loop. You lose the iteration, and then when you lose the iteration, your probability of success plummets dramatically. So we've really made the investment in developing our own tools for characterizing these systems.
So when you have that infrastructure for characterization and rapid prototyping, do you then make a trade-off in your ability to then scale things? Because then you're not using existing scaling things. I'm thinking of the analogy of semiconductors and when people used to prototype custom chips versus going to a major fab.
That we're at a really incredible time in history right now where you don't have to do that for most of the stuff. You don't have to do that anymore because you can buy an Arduino unit for $12 and you can program what you used to have to solder a PCB board to do.
Yeah, this is true in the material science of the food that you're working on.
For us, our entire office runs on Raspberry Pis and Arduino units that control controllers to measure different stuff. And the great thing about that is they are scalable because you just go buy another $40 computer that has a wireless card built into it that you can communicate from halfway around the world, hook a couple custom built peripherals into that, and you've scaled that system. So I think I would have agreed with you, 5-6 years ago.
Yeah.
But with basically the advent of, frankly, the Arduino unit, we've really been able to scale this. And 3D printing. So, all of our time-lapse systems are built with 3D printed components.
What's a time-lapse system?
Allows us to monitor the physical aging of fresh produce as a function of time. And this is like super nerdy if we're going to geek out.
Let's geek out.
I spent a lot of my PhD work using transmission electron microscopy tomography to view things on really, really short length scales, on nanometer length scales, and really look at things in really fine detail. And the time-lapse photography for me, feels like a different kind of microscope that allows us to kind of view the world without time in terms of produce aging,
Right.
which really has led to some really incredible realizations about the physical aging process of fresh produce that's led
Wow.
to some really interesting developments at the company.
You're literally compressing and adding an entire new dimension to your view because of the cheapness of being able to do 3D printing and all these other things.
We would not have been able to do this more than eight years ago, probably.
Yeah. I started in material science as well, and I eventually moved on to more of the software world because of the problem that you just mentioned, which is it's hard to iterate. And I always thought that material science was sort of confined to R&D. There was a really good time for material science, I think, a while ago with semiconductors, but I thought today it's mainly R&D. So, but I think because of some of the things you just mentioned, it's becoming possible to build a company based off of material science today more and more.
Yeah, where it's not just like a tool or a feature, but it is a core of a product. And I think the most exciting things in material science in general are things like, flexible electronics, the future of that. I mean, to me, all these things are interconnected because the thing that held a lot of this innovation back before in the past was that there was a lack of supply chain for materials, or the ability for different groups to work together, or systems to rapidly prototype and then figure out to scale. And when you have all these different companies now coming into the space, just material science being taken more seriously as a core enabler for new types of tech, it's kind of phenomenal what's possible.
Well, see, the funny thing to me is material science has been fundamental to us as a species. Look at how we've defined our ages. The Stone Age, the Bronze Age,
that's so great to
the
think
Iron
about.
Age, the Steel Age, right? Silicon Age. We define our development as a species by what material set we have available to us. I don't think it's that surprising that material science is becoming really interesting again, because I view material science as bridging the gap between what's available and what's useful. And how can you combine what's available to give you something that's useful and give you some new set of properties that enable some new advancement. The fruits are almost inconceivable of material science innovations. I mean, think about if someone...
you're saying fruit in an analogy sense, not like the actual literal fruits.
Right,
okay,
exactly.
let's be clear.
Well, okay, actually,
we all
in this
have
sense,
a penning disease in this room.
Exactly. It could be figurative or literal in this case for once. Imagine you're living in a society today and you invent steel, right? It's everywhere. It's everywhere on this planet. And so although the opportunities for gain in material science are just, I think, unfathomable almost, it's incredibly difficult to do because material science is generally or is such an interdisciplinary field.
That's exactly what I love about it so much. So if I could go back and do school all over, I would do material science in a heartbeat.
Well, the challenge is you can do so many different things in materials. You can be doing the chemistry. You can do the characterization. You can be doing the measurement. You can do the property stuff. You can do structural. You can do so many different things. And I used to say, I don't care how you make it. I just need have you show me the structure on paper and I can tell you what it's useful for. But that's a big problem, right? When you start talking about supply chain and building a business, okay, great. My skill set is around knowing what molecules can do and how to characterize them. I have no idea generally how to make them. Yeah. And so without being able to connect those skill sets, people who know what to do with them and the people who know how to make them and then manufacture at scale and then, do all this other stuff, it's really difficult to come together.
It's still a very hard problem. I wouldn't disagree. Yeah. In general, what are some of the interesting things you think are happening? Because I feel like people talk a lot about materials like graphene, and what are the things that are happening in the industry that are high level interesting to you in that space?
I would probably say the main breakthrough that will change a ton of technologies all across is battery technology.
Yeah.
Right. As if we can get higher storage, lighter, longer lasting batteries, that will change a lot, right? It will change everything from drones to VR to literally every industry. Mm-hmm. But that it's unclear if that will be a private company innovation or if that will be created out of a government lab somewhere.
Right. One of the things that's really interesting about material science is, unlike a lot of the other disciplines, and maybe because it is cross-disciplinary, it is the one where I still think a lot of government-led innovation funding is the most important, because they are the heads, they're the most interested in really thinking of the next generation of materials. And
they're training the people that are going to do the work.
Yeah.
Right. I mean, all of our team, we couldn't have hired straight out of undergrad and tasked them to do what they do for us now. I mean, they needed the training that came from government supported programs to do the core fundamental science that underlies what we're doing.
Yeah.
For me, I think the part that I really get excited about is in the field of additive manufacturing. I mean, I look at a 3D printer now and we use them in our office and, we're extruding a thermoplastic elastomer, out of a heated nozzle, and we're just basically making a structure and melting it and letting it dry. And I look at that and go, wow, who's going to develop the HP of 3D printing with the different inks that are all from material science understanding that allows you to print a fully functional, fully functional device? And we don't do that now, and maybe, with the combination of laser sintering and some other stuff. But if you start thinking about like combining chemistry and, mechanical engineering and robotics, which give you the 3D printing, with material science, which gives you the ink, I think the opportunities for doing, local manufacturing are just kind of incomprehensible.
The great example I think of is this initiative a lot of people from NASA to Autodesk that I've been working on, which is bringing 3D printing to be able to like recreate entire new structures in space so that you can actually build what you need. That's like local manufacturing on crack.
Yeah, no, exactly. And I think I think in the future, you're going to have a fancy 3D printer in your home, and how wealthy you are is going to be what type of 3D printer you have. If you're really wealthy, you can print the latest and greatest iPhone. If you're not so wealthy, maybe you can only print, shoes or something like that.
Well, let's close on talking about our vision for the future of food. What do you guys see the future grocery stores looking like? I mean, does this change what shows up on our shelves?
That's actually the thing that probably gets me most excited. There's a reason that if you, held up a dozen different kinds of produce, that most people could name those common dozen kinds of produce. But if you think about the genetic diversity that exists on this planet, there are millions and millions of different kinds of produce. The reason that you're not able to identify them is that you don't live in a region in the world in which they're grown, or you don't live in a region to which that those products are able to be imported into. And so, when I think about what happens is, when you look at what plant breeders do, basically is when they're breeding a new crop, they're looking down the list, and the number one thing on their list is transportability. And taste, nutrition is like level 12 or 13 on the list. It takes really significant investment for big companies to be developing breeding programs. And those breeding cycles are like 8 years long. And so you need to do massive investment to come up with these new varieties. And so one of the visions of the future that I get really excited about is the opportunity to extend the shelf life of a crop so that smaller produce variety can make it into a grocery store. And this is the same value proposition for a small organic grower in the United States as it is for a smallholder farmer in the developing world. Same thing with an organic farmer in the US. And one crop that we worked on that we never thought we'd work on are called finger limes. And check them out if you haven't picked these things up in the grocery store. They're natively from Australia, but they were brought into the United States, I think about 8 years ago now.
And it's good that the U.S. government didn't make them record a video to apologize for bringing them in. Sorry, I had to make that joke.
Yeah.
Do you guys remember what happened with Johnny Depp and his ex-wife now and bringing their dog to Australia? But anyway, go on.
That's pretty great.
Delicious with shellfish.
Yeah. Oh, yeah. So they're really interesting. They're actually another branch of citrus. But you cut them open and they look like caviar pearls, and each of those little pearls has a citrus flavor to it. I know that my finger limes, caviar limes, or cocktail limes.
Okay.
But they're really these incredible little citrus fruit. And the challenge with them is, they brought them in the U.S., they grow a bunch of them, but the shelf life of these things is like 5 days maybe. A supply chain that only lasts 5 days doesn't get you into very many stores. It's just not really commercially viable. Right. And so we've been able to extend the shelf life out to like 25 days.
What's normal in terms of so I grew up part of my life in Sri Lanka. Yeah. And what's normal here, apples, bananas, berries, is actually really rare there. And what's normal there is like papaya, mangoes, rambutan, all these things that people have never heard of. And some of them are just incredibly delicious, and more so than anything you'd find here. And you just don't get access to them here. So in some future world,
you can move that around.
You can move that around. And what you'll eat is not the most transportable food. It's just the best fruit.
Exactly.
Right, exactly. It's no longer constrained by only time or transport.
Exactly, and not just the best type of fruit, but the best grower, right? Mm-hmm. And fruit that's grown in regions that, for example, strawberries that's grown in Watsonville and bred in Watsonville, and now you're transporting that down into Mexico to grow. That fruit was optimized for growth in Watsonville, right? That genetic variety might not be the best one in Mexico, but because doing a breeding program in a bunch of, disparate places to match a local geography is so cost prohibitive, you just go with that. produce that's better suited to the growing environment that it's actually in. You can actually improve yields relative to what they'd be if they were bred in another environment.
And it just allows new entry points, like you said, for all different types of new players. It's democratizing access on both ends. And this is a theme that I love. But the other thing that, earlier you mentioned how you can do a map of all the fruit around the world and map the times and their perishability. And it reminded me, the image that popped into my mind is this map that makes its rounds on Twitter that's really popular, of countries organized by the most popular social network. It's essentially a way of showing this dissolution of borders and movement through technology. And what I love about what you're describing is you can now essentially remake that map that you described of all this produce and by perishable life, by shelf life and location, and essentially just move it all over and make time not matter.
Yeah, or not matter as much.
Or not matter as
right?
much. Yeah, I don't want to exaggerate it, but that's a pretty big effing deal. James, thank you for joining the A16Z podcast.
Thank you so much for having me.
Thanks.